Over the last couple of weeks, we've seen a whole bunch of convergence tests so that we can check whether or not a given series converges or diverges. And at this point, you might rightfully be wondering, who the heck cares about whether or not a series converges or diverges? And today, we're sort of going to get to the main point about why we would want to talk about series, which is the concept of a power series. And so instead of looking at a series as just a constant number, we're going to start viewing series now as functions. And the question will be, what type of functions can we represent as infinite series? And so a power series is just the fancy name for a function that is an infinite series. And really, these are infinite polynomials. And so typically we'll look at power series of the form a sub n times x to the n, and this is just shorthand for this infinite polynomial a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 times x cubed, and so on. And so it will turn out that a lot of functions that we know and love already can be represented as power series, which will just be these infinite polynomials. And we already know from Calc 1 or just from pre-calculus that typically dealing with polynomials is a lot nicer than dealing with other more complicated functions. And so the goal is going to be to explore how many functions can we write as infinite polynomials, and does viewing them as infinite polynomials make it easier to work with them? And the answer is going to be that we can write a lot of functions as infinite polynomials, and it makes it massively easier to work with them. And so sometimes we'll actually want to generalize what I just wrote, and we'll want to center our power series around a different value c. And so centering around a different value just means that we're going to write our polynomial a little bit differently. And so that's terminology for saying that our polynomial is just going to have x minus c everywhere instead of just x everywhere. And so it looks exactly the same otherwise. And so this phrasing of centering it should maybe remind you of when you talked about linearizations in Calc 1, and you would find a linearization of a function at a point or centered at a point. That's the same sort of terminology as here. And so one initial question that we might care about for power series is, when is it the case that you can actually plug in x into a power series and get a meaningful output? And you could tell that if every value of x that you plug in always gives you infinity, then that's not going to be a useful function. And so the power series that you're talking about is probably not a helpful one to use. And so, in other words, the question that I'm really asking is, for which values of x does a power series converge? And so in future classes, we'll see how to connect power series to functions that we know already. But the goal for today is going to be a little bit less ambitious, and we're just going to check for which values of x does a power series actually give you a number instead of just giving you infinity over and over again. And so the first power series that we'll look at is this series, the sum of x to the n. And so again, this would be shorthand for the function 1 plus x squared plus x cubed plus x to the fourth, and so on. And so now I need to figure out which x values this converges for. But really, we've already seen this series, and calling this variable x versus calling it a letter r doesn't really make a difference. This is still just a geometric series. And so that means that we know that this series converges if the absolute value of x is less than 1, and it diverges otherwise. And so we'll actually refer to the range of values where x converges as the interval of convergence. And so in this problem, the interval of convergence for this particular series is whenever, again, the absolute value of x is less than 1. That means that x would have to be between -1 and 1. And so I'm using parentheses here because if x is literally equal to 1 or -1, then the series will diverge just because the terms in this series don't go to 0. And so I need to have parentheses instead of brackets here. And the other terminology that we'll use is the radius of convergence. And so this will correspond to the fact that this value right here is equal to a 1. And so that's really telling you something about the width of the interval of convergence. And so in this case, the radius of convergence is going to be a 1 because this value right here was. That maybe seems a little bit vague right now, but after a couple more examples, you'll see what the radius of convergence is in general.